This is our pre-laboratory lecture for the synthesis of diphenylacetylene from trans-Stilbene. This is a lab that we're going to be doing this week in organic chemistry. So we're starting with trans-Stilbene, a diphenylalkene, and we're going from an alkene to an alkyne. And that looks like it's fairly straightforward in that you would only need to add one more pi bond. But we have to remember, if we look at this, right, here we have in the alkene a sigma bond and one pi bond. Right? Here in our alkyne we have a sigma bond and we have two pi bonds. Well, the only way to create a pi bond is to do an elimination reaction. But in order to do a standard elimination reaction, we need a leaving group. And all we have here as potential leaving groups are hydrogen atoms. Hydrogen atoms, if they act as leaving groups, would leave as a hydrogen with two electrons and a negative charge, a hydride ion. And a hydride ion is a very strong base, and so it makes a very poor leaving group. So we can't do a direct elimination because we've got a poor leaving group there. And there's no easy way to substitute a better leaving group for one of the hydrogens, right? So the big challenge here is, how do we introduce enough leaving groups to make the two pi bonds that we need to make? Well, the two pi bonds are really the hint. Right? So what we're going to do is introduce two leaving groups. So that we can make the two pi bonds needed in the product. Okay? Now, our favorite leaving groups are halogens. Things like bromine. So if we're going to introduce two leaving groups, we might think we could use molecular bromine as the source of the two bromine atoms to be our two leaving groups. Let's look at that reaction. It's a reaction we've done before. Right? The standard way we add bromine to an alkene is to use molecular bromine, which is nonpolar, and we dissolve it in a really nonpolar solvent that will not react with the halogen, something like carbon tetrachloride. And we've talked about the mechanism of this, and we'll go through it because we're going to use that mechanism even if we don't use this method. But we know that bromine adds, and you get, as a product, a vicinal dibromide. Right? And that vicinal dibromide puts a bromine next to a hydrogen. So we have a leaving group and a hydrogen on the alpha or on the beta carbon. That could do an elimination. And we've got another leaving group and another hydrogen on the beta carbon. So we can do a second elimination. So that looks like it solves our problem. But in this case, it creates a couple of other problems. One has to do with the bromine itself. Bromine itself is very reactive, and so we don't like to use a lot of molecular bromine. The worst lab accident we ever had involved, and this was more than 30 years ago, but it involved a student handling molecular bromine, not wearing gloves, even though the student had been told to wear gloves. And the student was holding the bottle of molecular bromine. Molecular bromine is a very volatile liquid. The heat of the student's hands boiled the bromine, It came out of the bottle, down the side of the bottle, across the student's fingers. And before the student realized, it had burned a hole in the student's skin down to the white connective tissue layer underneath. And a chemical burn like that is very painful and very slow to heal. So we try not to handle molecular bromine any more than we have to. So there's one problem. Making the solution would require us to use a lot of molecular bromine. Whether it's endangering the students creating those solutions, it's creating more danger than we would like in the preparation. So if we can avoid using that amount of molecular bromine, we do. So there's one problem. A second problem has to do with the solvent, the carbon tetrachloride. Now, carbon tetrachloride has been found to be carcinogenic. Now, it's not carcinogenic in small amounts, but it is carcinogenic in large amounts. It used to be used in dry cleaning. It would leak into the groundwater, and so there's lots of contaminated groundwater around because of carbon tetrachloride from dry cleaning. So there's a problem. Because it's carcinogenic, and because the chlorine makes it non-flammable, it's expensive to dispose of. Right? So using it creates an expense in getting rid of the leftovers. And again, as I've told you students before, I've got a couple of goals, right? One is to keep your tuition as low as possible, and one is to make my raise as large as possible, and saving money on disposal is one of the ways of doing that. A third problem with carbon tetrachloride is that both reactant and product are soluble in carbon tetrachloride. Now that doesn't seem like a problem, but we want to take this product and use it for something else, and so we need to be able to easily recover it. And since the product is soluble in carbon tetrachloride, it's going to make it difficult to recover that product. And so we'd like to use a solvent that avoids a number of these problems. So we're going to use addition of bromine, but we're going to do it in a different way. We're going to use a compound called pyridinium bromide. Pyridinium bromide. This is the pyridinium ion. It's protonated pyridine. And then the bromide would be a bromide ion, but perbromide means we've reacted that with a molecule of molecular bromine. It makes a tribromide ion. If we look at this, it has 1, 2, 3, 4, 5 regions of electron density around it. 5 regions would be trigonal, bipyramidal, but since only 2 of those regions are bonding regions, you get something that's linear with 3 unshared pairs around the equator of the trigonal bipyramidal structure. And so we're going to generate our bromine from the decomposition of this pyridinium bromide perbromide. Now, it has some advantages. One, as an ionic compound, it is a solid. And it's easier to handle than the very volatile liquid molecular bromine. Right? We can weigh it on a balance. We can handle it with a spatula. You still should wear your gloves as you're handling it, but it's much easier to handle than the volatile bromine. And it's also soluble, right? Another advantage is it's soluble in a polar solvent like glacial acetic acid. Glacial just means almost pure acetic acid in liquid form, right? So that's the pure form of acetic acid in the bottle. So glacial acetic acid is going to be used as a solvent. And one of the things that's nice about this is that our starting material, our Stilbene, is soluble, at least when the glacial acetic acid is hot. Our vicinal dibromide product is insoluble in the glacial acetic acid. And so therefore, we can easily isolate it. We can easily isolate it by filtration. And as far as disposal, glacial acetic acid is something that is a food product. It's just very concentrated vinegar. And so when diluted, it can be disposed of easily, and it is biodegradable. And so that solves our solvent disposal problem. So doing it this way solves a number of the problems we identified in the previous slide. And so in the glacial acetic acid, we get a decomposition of the bromide per bromide ion, right? A bromide ion acts as a leaving group, leaves behind molecular bromine. This is an equilibrium reaction, but the molecular bromine is consumed during the addition reaction. That consumption of the molecular bromine drops its concentration in solution. That pulls the equilibrium toward product to replace that, right? Who's our second favorite dead French chemist? Le Chatelier, right? Le Chatelier, we're going to use Le Chatelier's principle as we remove molecular bromine on the product side. The reaction will try to replace that to maintain the equilibrium, which gives us more molecular bromine to consume during the addition reaction. So the bromine will be developed in situ, right? Here's your college word of the day. In situ, right? In the situation, in the reaction mixture to be consumed as we make it. Then the addition of bromine to the trans-Stilbene goes by our standard mechanism that we learned for the straightforward addition of bromine. The Stilbene alkene, the pi bond of the alkene, acts as the nucleophile, right, to attack the bromine. The bromine also acts as nucleophile to replace the electrons as a partial positive charge is trying to develop there. The electrons replace there. We get a cyclic intermediate. Dissociation of the second bromine atom leaves behind our cyclic bromonium intermediate. In that cyclic bromonium intermediate, the bromide ion attacks one of the two carbons as a nucleophile. That bond breaks with bromine acting as a leaving group, but still attached by a bond here. And we get, because of the stereochemistry of the starting material, and you can build this and look at it if you want to prove this to yourself, right? Our product compound is a meso compound, right? It is the two ends. If you rotate this, are mirror images of each other, right? If we rotate this, you'd have bromine on the top, phenyl group in front, hydrogen back, phenyl group in front, hydrogen back, and you would have a plane of symmetry right there. So it is a meso compound, right? So it is the meso compound of 1,2-dibromo, 1,2-diphenylethane, right? So that's the product of our first reaction. That will be insoluble, we will filter it out, and then we will use that product for the second part of the reaction, the elimination of the two new leaving groups we've introduced to create the 2 pi bonds in the alkyne. All right. So, we're going to make an alkyne. And normally making an alkyne is, the second elimination is more difficult than the first elimination to make an alkene. So normally when we make an alkyne, we have to use either stronger bases than we needed to make an alkene, and or higher temperatures. But we have an advantage here that we've created to make this a little easier. Right? If you note, we've got a pi bond, a sigma bond, a pi bond, a sigma bond, a pi bond, a sigma bond, pi bonds, sigma bond, pi bond, sigma, pi, sigma, pi, sigma. Right? So in our product, right, the carbon-carbon triple bond is conjugated with other pi bonds. That tends to stabilize it, right? That makes it more stabilized, therefore easier to form, right? So we're going to take advantage of that. So because we've got that stabilized system, we can use a more standard base like potassium hydroxide rather than using exotic bases like, sodium amide, right? Which would be the more typical choice to go from vicinal dihalide to alkyne, right? So we can get away with the weaker base. But we're still going to have to do something about the temperature. And so what we're going to do is we're going to do this, we're going to use ethylene glycol as our solvent. Now, right, we're going to reflux this. And remember, it is the solvent boiling point really is the thing that determines the reaction temperature during reflux. So we've picked a solvent with a fairly high boiling point that will promote the reaction, right? This slightly more difficult reaction by increasing the temperature as it refluxes. And because of that high temperature, we're going to reflux it with no water in the condenser. Right? We're going to reflux it with no water in the condenser. Just airflow will keep the condenser cool enough to keep the ethylene glycol from leaving the condenser. Okay? So we're going to set up our reflux apparatus. We're going to do it without running water through it, and we're going to get formation of our alkyne. So let's quickly go through the mechanism of that. It's what we would expect. Right? If we're looking at this mechanism, this is a typical E2 reaction. And I've drawn this so that our hydrogen, right, our beta hydrogen, and our leaving group are anti to each other and coplanar. Right? If we looked at the Newman projection of this, right? If we looked at the Newman projection of this, I can draw it. If I rotate the left forward, that's going to put the phenyl group there, the bromine on that one there, the hydrogen down, right? That's the left carbon. Then the right carbon, bromine is going to be up, phenyl is going to be there, and hydrogen is going to be there. Right? And so we end up with our leaving group and our acidic hydrogen. Right? In the same line. Right? They are planar to each other and they are anti to each other. And so that is the optimum geometry for an E2 reaction. Now, our product then is going to be a vinylic bromide, right? But again, because of the pi bonds in the phenyl rings, the pi bond of the alkene is conjugated with the systems in the phenyl rings. That makes subsequent reaction easier than we would expect for a vinylic bromide. And so at our high temperature, and with sufficient potassium hydroxide as base, we can get a second elimination of the vinylic bromide, again, where as hydroxide ion is taking hydrogen, electrons are falling down, bromide ion is leaving, again, in something that is very much an E2 limiting reaction, and then we get our diphenyl acetylene, which if we draw the full structure, looks like that. Now, the ethylene glycol is soluble in water. It's easily removed. The product is easily isolated. But then we need to do a purification recrystallization. Now remember, the book says something like recrystallize from some volume of warm ethanol. Now, when they say warm ethanol, in this case, one change from what we normally do, we are not going to boil our ethanol that's going to be our recrystallization solvent, right? We want it somewhere in the range of of 35 to 45 degrees Celsius. You should be able to touch it. It should not be too warm to touch. Right? We do not want it boiling. Okay? You want it warmed on a hot plate to 35 to 45 degrees Celsius. You're going to add it dropwise. Until the product just dissolves. Okay? Again, keeping it warm. Now, part of the problem is, in this warm ethanol, our product is more soluble in the warm ethanol than is normally needed for a recrystallization solvent. We need something after we've got it in there to reduce its solubility suddenly. And so to do that, we're going to add water. We're going to add water dropwise. Something about up to 1 milliliter. Don't just dump 1 milliliter in there. Add it dropwise until the solution gets cloudy. Then we're going to put it on the ice and collect the crystals. So we're going to modify our recrystallization procedure just a little bit. So this is your pre-lab lecture for the first lab that we're doing this coming week. You do need to come to lab prepared on Monday and Tuesday. If you have any questions, please let me know.